Hi, so my name is Chris. I'm a software engineer with Apex AI. Today I'm going to talk about ROS2, our experiences applying it to the problem of autonomous driving, some of the lessons learned and limitations we found in ROS2 for autonomous driving, and how we're trying to fix that in our product Apex OS, which is an automotive grade subset of ROS2 for safety critical systems. First off, just to get everybody on the same page, autonomous driving is the next big technology that promises to transform the world. So it'll change the way we move around, make the world a smaller place, really reshape industries so companies will live and die, and along the way, people will make a lot of money, hopefully myself included. But for all of the promise and hype in autonomous driving, at the end of the day, it's just a big robot. So it's a robot because it's got sensors, LiDAR, camera, IMU, GPS, radar. It's got actuation, throttle, and steering. And in between the two, there's a bunch of algorithms. So that comprises a pretty standard robot. The big part of big robot comes from the fact that a car, and thus an autonomous car, is about 2,000 pounds or 1,000 kilos. It drives around at 30 meters per second, which is about 60 miles an hour, or 80 kilometers an hour. So that's something really big, moving really fast. And if something goes wrong, then it can and will cause a lot of damage, injury, or even death. So I hope all of you will agree with me that autonomous driving is an application where safety is of the utmost importance, or in other words, autonomous driving is a safety critical system. That said, the question that my company spent the first 6 months of its existence trying to answer was, can we use ROS2 to build an autonomous driving vehicle? Where I hope I've established that an autonomous vehicle is a large robot in a safety critical system. To cut a long story short, answer to that is yes. And we can say yes because we actually went ahead and built an autonomous vehicle using ROS2, and you can actually see it running in these videos. Of course, this yes comes with a couple of caveats. One is that our autonomous vehicle is not the highest level of safety that we would be happy with, and second is that we actually didn't build the entire autonomous vehicle using ROS2, only ROS2. We're a company of about 15 people, not hundreds, so we can't really build the entire autonomous driving stack in ROS2. Caveats aside, let me just introduce you guys briefly to our autonomous driving setup. So on the left-hand side, you can see our car, which is a Lexus 450h, outfitted with drive-by-wire power and steering and other sensors by Autonomous Stuff in Morton, Illinois, USA. On the right-hand side, you can see our trunk setup, which has a bunch of power and 2 computers connected by a 10 gigabit Ethernet switch. In a little bit more detail, here's our computational setup. So on the left-hand side, we've got an NVIDIA Drive PX2, which is an ARM-based production intent ECU. On it, we've got a couple of algorithms running. So we've got a 3D object detection stack and a tracking and prediction stack, both of which are written by me. These are built against ROS2, and they produce some outputs, which are transmitted from the NVIDIA Drive PX2 to the other computer via the 10 gigabit Ethernet switch. These are converted from ROS2 to ROS1 messages using OSRF's ROS1 bridge. These ROS1 messages are then taken up by a heavily modified version of Tier 4's open source AutoWare, which is written in ROS1. So all of these ROS1 nodes are running on top of the Intel Spectra, which is basically a somewhat ruggedized workstation that you'd more or less find in your office day to day. So one of the takeaways I hope you guys get from this is that we have successfully built, and you can also build, a combined ROS1 and ROS2 system. The second point I want to get across is that if you've got a lot of legacy code in ROS1 and you're interested in using ROS2, don't let that scare you, because you can actually move things over from ROS1 to ROS2 just bit by bit and still have a fully functioning system. A second takeaway I hope to get across to you guys is that based on our experiences, ROS2 is more or less ready for the big time. So if you want to build a large robotic system with ROS2, you can actually go ahead and do that now. So if you're familiar with the 5 Cs, ROS2 already has 4 of the 5 Cs. The only thing missing being computation or algorithms. On top of that, ROS2's got a number of additional nice features like lifecycle nodes, deterministic launch that they talked about in the previous talk. That said, of course, there's a number of good reasons to keep ROS1 around, so there's a lot of tools and algorithms still available in ROS1. But you can use this with the ROS1 bridge together, as we did in our setup. And over time, I'm sure these tools and algorithms will be ported over to ROS2. So, I hope it got across that I'm a big fan of ROS2. It's fantastic to work with. That said, for the problem of autonomous driving, which again I stress is a safety critical application, ROS2 is not quite 100% there yet. So there's a couple of big areas that ROS2 is lacking in. One of which is hard real time, which I'll talk about in a bit. Second are security and robustness mechanisms, which you saw from the previous talk. There are some security and robustness mechanisms, but for a safety critical system, you need many, many more. Lastly, there's testing and certification, for which there's some testing, but no certification. But don't let this steer you away from ROS2 if you're in autonomous driving or any other safety critical application, because my company, Apex AI, has its flagship product, Apex OS, which is a safety critical version of ROS2. Surprise, surprise, this is marketing. Marketing aside, though, the first and probably one of the most important things you need for a safety critical system is hard real time. So a hard real time system is one that takes in some inputs and it will produce a deterministic output, and it has to do this in a given time span 100% of the time. So it's deterministic both in the input output but also its resource consumption. In practice, the way that you achieve a hard real time system is basically two things. One is that you need to make sure your application is static. So all resource allocation happens outside of the runtime loop. Second, you need to make sure that your critical path in your code is finite. So that means it's got a finite and tightly upper bounded number of operations, and each of those operations can execute in a tightly bounded amount of time. With respect to this, ROS2 is still a little bit too dynamic to support a hard real-time system on top of it. So a couple of the sort of hard real-time sins it commits is that there's still some memory allocation. So one important place here is when they're handling a subscription callback, which is a very important pattern. So they allocate memory to catch the message. On top of that, they also make use of some constructs which allocate memory, such as std string, std exception, and so on. Memory allocation in general is an example of a blocking call insofar as it's non-deterministic in its execution time. Other examples of blocking calls that are also present in ROS2 are file I/O, which they use for logging, and I'll talk about how we replace that in a bit. Finally, all of the DDS implementations that ROS2 is built against, that are publicly available at least, are not real time. So what we're doing at Apex AI is that we are making ROS2 static, so we're moving all of the resource allocation outside of the core runtime loop. Second, we're making sure that all the non-real-time components are replaced with real-time components. So that means either swapping them out in bulk or swapping them out at the micro level. For instance, making sure that the mutexes don't block infinitely so that they can time out. On top of that, we're also making sure that ROS2 can be built against various real-time DDS implementations. So one example of a non-real-time component that we swap out for a real-time component is the logging. So by default, in ROS2, the logging macro expands to some function, which by default calls fprintf, which is file I/O, and a blocking call, which is not okay in a hard real-time system. By contrast, what we've done is we've redirected this to our real-time logger, which uses atomics to shuffle a message into a shared memory ring buffer, which is then deterministic because it's an atomic. And then this buffer can then be fleshed out with an idle priority thread, either to disk like a black box or to console. So then that idle priority thread won't affect the greater running of your whole system. Another thing that we've also done is we have provided an alternative to the ROS2 callback, because as I noted earlier, the ROS2 callback allocates memory. What we've done is we've modeled our sort of callback alternative on the wait set from the DDS level, which is similar to a Unix-style select call. In addition to being static, this alternative pattern basically also promotes two important things that you won't necessarily think about with a standard ROS2 callback. One of which is deterministic, is execution order of your operations on your messages. And second is, what do you do when your messages don't arrive in time? How do you react to that? So in a hard real-time, safety-critical kind of system, you need to think about what you do with these, what you do when your messages don't arrive in time. You can, of course, do these things with a standard ROS2 callback, but they don't necessarily lend themselves well to do that. So there's a lot of, it would require extra discipline on your part. Another thing that we are doing, which is somewhat tangentially related to hard real time, is large memory support. So in autonomous driving, there is a number of large messages flying around. For instance, point cloud messages or camera images. These messages can easily be on the order of a megabyte or more in size. And with network-based inter-process communication, as these messages get larger in size, so too does the flight time of these messages. So with these megabyte or more sized messages, the flight time can be very non-trivial, for instance, on the order of tens of milliseconds or more. What we've done then is we've implemented a shared memory transport prototype, and we're working with some DDS vendors to formalize this. What this buys you with respect to real time is that it reduces the flight time of your large messages by an order of magnitude or more. What this then buys you is it reduces the latency in your entire system and then gives you a lot more headroom to hit your hard real-time deadlines. If you're interested in how we kind of did this benchmarking and figuring out where the bottlenecks came from, I highly recommend you listen to my colleague Andreas Pasternik's talk, which is later on in the afternoon. Second, ROS2 has some robustness mechanisms. So they introduced the lifecycle nodes in the previous talk, and William has a talk on ROS2 launch in about 40 minutes, I think. So these are great mechanisms that are not present in ROS1. So they make sure basically that your node is in a good state when it initializes, and it makes sure that it can handle some perturbations and make sure that your individual nodes are in a good running state. That said, with a safety-critical system, you always need more robustness mechanisms, and we're working on adding more of those things in. So some of these things are, for instance, like heartbeats to detect silent failures, or other higher system-level robustness mechanisms to make sure you can recover from somewhat larger faults. On top of that, we were also looking at security. So again, they also introduced security in the previous talk, which was a great introduction. But unfortunately, security is sort of a never-ending battle. And to ROS2's credit, as an organization, they've introduced security from the get-go. But unfortunately, a large robotic system is not just DDS. So there are more forms of security that you need. What we're then doing is we're trying to sort of patch some bigger holes and catch some low-hanging fruit that's easy to fix. For instance, we're adding an executable whitelist to our operating system to make sure that you kind of block against some malicious participants. And on top of that, we're also working on some security mechanisms that are important for the autonomous driving use case, which is, for instance, over-the-air updates, secure key storage, making sure we can integrate with existing security solutions, so we don't reinvent the wheel or something like that. Finally, the last thing I'm going to sort of trash ROS2 about is testing and certification. So I talked a lot about like safety critical applications and all that stuff, but one sort of elephant in the room is how do you prove that your code is safe? So short of having a relatively simple use case or problem, which I hope most of you can agree with me that autonomous driving is not that simple, and using formal methods, you can't really prove that your application is safe. What you can do, though, is you can follow a functional safety standard to the letter, and in doing so, you can make sure that your code hits some minimum level of quality and presumably then some minimum level of safety. So broadly, ISO 26262 is 3 steps. So one, it's analyzing your use case. So here, unfortunately, ROS2 falls short because, they're use case agnostic, whereas we're a company, so we have no such limitations. So we focus mostly on the autonomous driving use case. Second, you follow a strict development process. So here, ROS2 is fantastic. Two things that are not quite there yet is, for instance, one is, I think most of us can agree that ROS2's documentation is a little bit raw still. And second, they don't explicitly follow a safe coding standard. So for us, we've been following MISRA C and C++ from day one. Lastly, you have to write and run lots and lots and lots of tests. So here again, ROS2 does great. They've already got unit integration tests, but there are a number of more tests that need to be run, many of which are driven by your use case, again, which ROS2 does not have, such as requirements testing, full stack testing, hardware and loop testing, and so on. Finally, you also need to make sure that your tests sufficiently cover your code by taking metrics. This means like line, branch, MCDC covered, and so on. We're actually working with ROS2 to make sure that they can actually get that in. Lastly, one thing I want to stress then is that at Apex AI, we're very, very dedicated to testing. So on the bottom right, you can kind of see that we've got our lab setup. So that's a lot of expensive hardware and sensors for a very small company, wholly dedicated for the purposes of testing. On top of that, we've also got our CI pipeline, which again is also very overdeveloped for a 15-person company. So we do static analysis, testing, coverage, cross-compilation, and so on every commit. That said, I mentioned like, oh, our product Apex OS, this and that. We do recognize that we're standing on the shoulders of the open source community. So wherever possible, we are giving back. So we've open sourced a number of tools that we've developed in-house, algorithms too. On top of that, we're also upstreaming a number of features and bug fixes as we find them to the ROS2 mainline. And I should mention that all of these are links, so when you get that later on. One last thing I want to mention too is that all of these things that we're doing in ROS2 to harden it, make it static and real time and all that good stuff, we're also doing for algorithms and other building blocks of the autonomous driving stack. So here are some of the things that we're doing to fix up the Velodyne driver, which is the backbone of our current 3D perception stack that you see running on the bottom there. Again, it's very raw. So that is basically what I've got. In short, ROS1 is fantastic for developing a large robotic system, but short of a full rewrite, it can't be automotive grade. That said, that's what we have ROS2 for, which is a full rewrite of ROS. At this point, I would say it's stable enough and feature complete enough for you to do some serious development against, and you can use it with your legacy ROS1 stuff if you want to. And it's very close to automotive grade, and that's what we've got Apex OS for, which is hard real-time, secure, safe, robust, and certified. Last thing, if anything I said interested you guys or resonated with you, feel free to reach out because we're always looking for more talent. That's all I've got, so thank you.
You mentioned over-the-air service updates.
Mm-hmm.
I'd be curious, have you done any experimentation with attestation using ROS2 where like two systems are negotiating and whether the other party is still maintaining an integrity in its like trusted execution environment?
Mm-hmm.
So like if you had the computer in the autonomous vehicle verifying that the LiDAR sensor hasn't been modified.
Mm-hmm. So let me preface this by saying that I am probably the only guy not working on framework at Apex AI, and that's it. I think we haven't done any major experiments with the security stuff, so we're currently still building that stuff out.
I see you've gone to a great extent to obviously build real-time extensions to ROS2. I'm wondering, as part of your safety standard, do you have redundancy in place? And is there any consensus in case you have processor failure?
Yeah, so that's one of the things we're considering and working on right now, because right now we're just working on getting ROS2 as it stands to be like static in real time, so hard real time. So right now we're mining our P's and Q's. So like, for instance, what you are doing with your Astrobe, just making sure like, hey, I can localize first. And then we're going to build that up further as we get more resources and time.
Is that part of 26262, that redundancy requirement?
I don't think so off the top of my head. That's more of an aerospace thing.
Oh, okay, cool, thank you.
So thank you very much.